So perhaps we can start. Welcome everyone to the 7th BTR conference. We are very privileged to have keynote speaker, Professor David Levinson with us today. But before actually I start the introduction, I would like to give a brief introduction about BTR for those who's who are not familiar with BTR. So we, Professor Kara Kokelman and I myself, we started the BTR conference in 2019. It was before COVID. And the rationale behind this online conference was because of my nationality, and again, because of lack of enough funding, I was not really able to attend the TRB conferences every year in the United States. And we were chatting that I was kind of talking to Kara, and I said, I have a paper every year, but I can't really go because, well, first of all, it's very expensive. Second, I'm not really sure if I get visa. And then I can kind of imagine, I don't have any kids or any disability, but I can imagine that's the too much actually of hurdle going to conferences if you perhaps have any caring responsibility or any disability. Then we actually decided to run an online conference. At the time, it was before COVID, it wasn't very common. However, after COVID, actually it became very popular. So I appreciate that, we all are having kind of, or perhaps suffering from Zoom fatigue or online conference fatigues and lack of concentration during online presentations. But again, I think that's a very good opportunity because the BTR conference is free, is low carbon. We acknowledge that we have still some carbon on the Zoom servers, but again, like considering all of the transport and all of the hassles of trips, we have eliminated actually a very big portion of the carbon of our travel. And I think it's a very great opportunity for developing and underdeveloped countries also to share their research with everyone without actually being worried about registration fee of the conferences, which is too expensive. Even for me that I live in Australia, I think that this is very expensive. So let's just contribute and continue to contribute to BTR conferences with sharing high quality research with our peers and contributing for the reviewing and all the actually activities associated with BTR. A very big shout out to Jason Hawkins and Giancarlos Prodi for co-chairing this conference this year, to Kara for all of his support, to our Zoom coordinators, amazing students of Mehmet, Dr. Mehmet İlrimoglu at the University of Queensland. So we have Nasser today as the Zoom coordinator. They have done amazing work in the last few years. Before actually I introduce David, although many of us know David and we have been following David's amazing work, I would like to play a video in the memory of Professor Hani Mahmassani. Basically missed and we lost one of the prominent professors of transport, Professor Hani Mahmassani from Northwestern University this year. And this video has been prepared by his student, Dr. Miad Sabari from the University of New South Wales. And let's just look at this video for 3 minutes. Okay, thank you so much. I will actually share the full file of the video if you want to go through the notes. And I think that's the time to introduce Professor David Levinson. We are very privileged to start the BTR conference this year with the keynote speak by Professor Levinson. So Professor Levinson is a professor of transport engineering at the University of Sydney's School of Civil Engineering, where he leads transport lab. He received his PhD from University of California, Berkeley in transportation engineering. His research spans transport engineering, planning, policy, economics with a focus on land use transport interactions, accessibility, and network evolution. He has published over 300 papers and multiple books and has made influential contributions to accessibility theory and transport system dynamics. I myself actually follow his LinkedIn posts and newsletter, and I encourage actually everyone else to do the same. So before actually I spend all of 1 hour, without further ado, I just hand it over to you, David. So I stop sharing.
All right.
Thank you.
Thank you. And now I get to share my screen. Hopefully everyone can see that.
Yes, we can see that. Thank you.
So before I begin, I'd like to note that I too am an academic descendant of Hani Mahmassani. My master's degree advisor was Gangwen Chang, who was Hani's first PhD student, I think, at UT Austin. And second thing I'd like to note is I am coming to you from the lands of the Gadigal people of the Eora Nation in Sydney. We like to acknowledge the traditional owners of the land here in Australia, and I'm sure in some other parts of the world. So I'm going to talk about a web of nets, which is based on a book that I wrote. You can buy this book where fine books are sold, but more importantly, you can download it for free from the University of Sydney Library, if you like what I say. This is a work that I completed last year with Samrita Sarkar, and of course help with various internet technologies as well. And so I'm going to start with the idea that everything is a network. Everything is connected. And this goes from the smallest scale, certainly levels of neurons we're all familiar with, to highways, which as a transport conference, probably we focus on more, from markets to galaxies. And all systems can be represented in terms of elements in their connectivity. All such systems can be thought of as networks. All networks can be represented by graphs, enabling analysis of their structure, dynamics, and behavior. And we want to understand the world from the point of view of networks, because if we can understand how these networks are structured and how they operate, we can transfer knowledge between fields. We're looking for universal principles. We're looking to be able to do innovation in one sector based on analogy with another. And we have this in traffic. The very first models of traffic flow came out of hydrology and water and pipes. It'll help us with problem solving. It'll help us with modeling and simulation. It'll help us in optimization and understanding how these systems work under ideal circumstances and less than ideal circumstances. Ideally, we can learn from mistakes and learn from mistakes in one field when we're designing another. And this kind of framework, I think, is important. And it's something that transport researchers learn typically in graduate school, but it's not something that we learn earlier. And I think it's something that we should be learning earlier. So Louis Sullivan, a famous American architect, the advisor to Frank Lloyd Wright, his mentor, said, form ever follows function, and this is the law. We have a function of a system, and the form of that system comes after it. He was talking about aesthetics of buildings primarily, and that we should design our buildings so that they're functional, and then we can put decorative elements on it, and the form, the outside of the building, comes after the function. But we can also say that function also follows form. in that that form of the building will shape how we use it, or the form of anything will shape how it is used. Function follows form. And I'm going to make another claim that the function of every successful network is to improve accessibility, broadly defined. And basically that means enabling one thing, a person, energy, matter, information, force, to reach or escape some other things. So escape is basically reaching the absence of the thing with the least effort or action or time or cost. Right? So this is what accessibility is in transport literature, enabling us to reach opportunities at some cost, measure how much accessibility we have. This is really a general principle. And the networks which do this better are more likely to survive. They're more likely to be reinforced or more likely to reproduce. Okay, and we can think of networks as having evolution, and how that evolution occurs depends on the context. So network can be engineered. All right, the National Interstate Highway System in the United States is a classic example of an engineered network designed designed originally in the 1930s, ultimately funded in 1956 under the Eisenhower administration. And it's more than just lines between cities. Of course, there's design standards for how wide lanes should be and the grade of individual road segments so that the grades aren't too steep, and curvature and pavement materials and lighting and all sorts of things that are designed. And it connects travelers across the US. And you might know it was the National System of Interstate and Defense Highways. It was originally designed to be able to enable the US military to move rapidly across the country. And this is something that Dwight D. Eisenhower, who before he was president and before he was commander of Allied forces during World War II, and the aftermath of World War I, had tried to drive across the United States with a number of military units before there was an interstate highway system, before there was even a paved US highway system. And he saw how difficult it was. And so this is something that he understood from a long period of time. So although it was officially established in 1956, the seeds of it were taking root in the 1910s. The internet. Now, the internet's an evolving system. Elements of it are designed, but it's a decentralized and self-organizing system. There is no one master architect of the internet or even an agency that's responsible for designing internet links. People can connect to the internet if they want to. It has engineered standards, but it's an evolving network. All right. We can look at it in the context of the US historically, but today we have, internet links across the oceans, and I'm sure that I am coming to many of you across the ocean and on one of these cables. There are evolved systems. Okay, there's lots of examples of evolved systems. This is a drawing of the digestive system, courtesy of DALL-E, an AI. I am not a medical doctor. I do not know if this is even close to correct as to how my digestive system works. I'm sure it's not really to scale. But it's an evolved system for processing food, and it's a network. In some ways, it's a simple network. Everything comes in through the mouth, and everything goes out through various sources and so on. But it processes food along the way. And then we have something like the cosmic web, which is an emergent network. And this facilitates the movement of matter and energy. And this presumably wasn't designed. So there's no evidence of a designer of the cosmic web. It came out of the Big Bang, but there's structure to it. It's not just random points in space. There are connections that are between blobs of matter and energy, and those connections are self-reinforcing, that the gravity along these pathways is attractive to other matter, which reinforces the amount of gravity along these pathways. So a network comprises interconnected parts that are engineered, evolved, or emerged to facilitate the transfer or sharing of resources, information, entities to support those interactions and flows between its components. And on your left is a simple network graph. In this case, there are 4 nodes. There are 7 links. I say it's a simple network graph. Technically, it's not a simple graph because there are multiple links between individual nodes, and we'll talk about multigraphs in a moment. But those nodes themselves can be networks. So we think about at a higher level of abstraction, connections between places. But then if you look at a node in a junction on a street network, it itself is a very complicated network where there are vehicle movements and potential conflicts, pedestrian movements and potential conflicts. All the circles are conflicts in the diagram on the right. And so what can be represented as a single node at a higher scale can be represented as a network in itself at a smaller scale. And a city is a node in a connected network of cities. Today, I guess the first city wasn't really connected with any other cities because somebody has to be first. And it is a network of networks. And so the image of the Kowloon walled city before it was taken down is itself a very complicated, multi-layered, multifaceted set of networks for movement of people and goods and trade, and a giant superstructure in a way that emerged from a lot of individual decisions, and certainly no one person planned all of that. Networks don't have to be the presence of something, they can be an absence of something. So the desire line shown here on the University of Minnesota campus is a network that's the absence of barriers, right? I mean, it runs along the earth, but the reason it is effective for people to keep using this same space is because other people have compacted down the earth in that location and cleared away the grasses and brush that had been planted there to discourage travel. And there's lots of networks as absence, animal trails, just human trails, pedestrian paths, rivers, the absence of barriers for the movement of fluids, cracks, orbits of planets in space, which have cleared out other, I mean, the definition of a planet is that it's cleared out a smaller, all of the smaller bodies around it that are not in orbit of it. So they have all collided with the planet historically or are in orbit of the planet. And you could also think about properties like filters and obstructions, which are different, as other ways of thinking about aspects of networks. Space and networks are inherently unequal, always and everywhere. Okay, so there is no equity to be had. Okay, you might try to make things less inequitable, but space is about differentiation. And a network is a differentiation across space, and it's a place in space where you can have a lower cost. You can move more efficiently over the network than not over the network, and that's why we call that place the network. A place is a differentiated space with greater concentration of opportunity. So a city is a place because it has more opportunities than the places that are around the city that have less opportunity, the areas around the city with less opportunity. An event is just a differentiated time with a greater concentration of opportunity. You go to a fair because all of the other people are there at that time. So we can think of a number of elements. If you go to the network science literature, they like to analyze networks statistically, and they define various things. We have nodes, we have links, we have couplets, which are pairs of nodes that aren't necessarily links. We have communities, which are sets of links that are connected to each other. We have the whole network. These are all elements of a network, and we can think about lots of different types of network elements. So I'm interested in accessibility, especially transport accessibility. And there's a famous quote from John Wheeler, a physicist: space-time tells matter how to move, matter tells space-time how to curve. All right, so there's an interaction, right, between the network lattice that is space-time, okay, and it's drawn as a network lattice here. The question is it really a network lattice? There's people who believe that it really is a network lattice. There's other people who think it's a continuum. But if we think of it as a network lattice as drawn here, then the lattice, objects in this lattice are attracted to each other because of gravity, and the well of gravity that Einstein talked about originally is showing the direction of that things would like to move in space. And then, of course, those objects themselves create gravity, which affects how other objects are going to move. And this is very much the same thing as accessibility in the transport literature. Networks tell people how to move. People tell networks where to serve. So how are you going to move? If you're a person in Chicago and you want to go into the CBD, near a transit line, and you might take that transit line, and places along the transit line have higher accessibility, opportunity to destinations, in this case, jobs in the morning peak period. You're more likely to travel along that network. So it's telling you how to move. But where the people are is where the network is going to go. And the question, of course, is the network alive? Is it making this decision by themselves? No, I mean, it's making this decision through agents. And those agents are generally, in the case of transport networks, generally human beings. But there is a process and a set of rules by which this happens, which we'll talk about more later. And so in accessibility, the only reason to be anywhere is to be near things or be far from things, or which is to say, to be near the absence of those things, and to own things, to possess things. And physical accessibility, we can have a variant of the Hansen equation here. The accessibility is some function of the number of opportunities you can reach multiplied by some measure of the impedance between places. All right, so typically we'll look at it as it's inversely related to the cost, and it's positively related to the number of opportunities that you can reach. And the accessibility at a given point is the sum of that. Okay, and we can make this complicated or easy, but just we'll keep it easy for the purposes of this presentation. Electric grids have the same idea, where we're looking at how easy is it for energy to travel between producers and consumers. And so you're looking at a system that was, the elements of it were all designed individually. I don't think there was one person who 50 years ago came up with a master plan for Sydney's electric grid. There was an initial connection, and then there's a series of incremental decisions afterwards, which enabled this to work. But it hasn't necessarily been optimized, but the whole world has been built around this. So given where supply substations are, the links are in the logical place, and given where the links are, the supply substations are in the logical place. The food web is an accessibility graph in a way. And what food consumers are fit if they maximize access to the food they prefer to eat. So humans want to eat cows and pigs and corn and other types of things. And so they design a system for that, but cows and pigs and corn have to get energy as well. And so there's this whole circular system. And this is abstracted, but you could draw it out for any individual human and see what they eat and see what the things that they ate, and so on and so forth. And we have this with water networks. Broadly, on Earth, there is the sun, which is emitting solar radiation, which causes evaporation and clouds, which precipitate water into rivers and lakes, which run off into the oceans, which then evaporate, and so on. It gets more complicated. So rivers are carving out paths of least resistance, and water is seeking the easiest route at any given time. And sometimes the easiest route is to evaporate, and sometimes the easiest route is to precipitate, and sometimes it is to recharge the aquifer, and sometimes it is to discharge from the aquifer, depending on the relevant pressures at the time. And lightning is a network, okay? So a lightning bolt is a complex thing, and it has a structure. It is a transient network. It only exists for a very short period of time, but there are lightning bolts that have branches, and they are traveling from what we think of it as from the cloud to the ground, but then there are upstrokes back. There can be intra-cloud lightning strikes, and so on. There's a lot of different aspects to this. So coming back to the cosmic web, the pattern of energy and matter that are moving away from the center of the known universe on the path of least effort. So the energy and matter are the travelers, and they're forging a path via gravity. Okay, so they're following previous travelers because of gravity, and they're forging a path for future travelers because of the gravity that they themselves emit, for lack of a better word. And this is a reinforcing type of system, so long as that there's that initial, there's the source of energy and matter at the center of it. What causes that beyond the scope of this little presentation. So we saw Kowloon Walled City. This is a cross-section of Kowloon Walled City. You can see transport paths in there. You can see plumbing networks in there. You can see other types of networks in there. Cities are multi-layered, multiplexed machines for access. And cities exist because they enable more to be done with less effort. And these layers include infrastructures, which we're familiar with as transport people, markets, economics, social networks, defense networks. So one of the reasons to be together, and particularly behind a walled barrier or a fort, is for common defense. On average, you're probably safer being surrounded by a group of people inside of a city than you would be just on the outskirts of the city. Governance can be organized better if people are closer together. You may be able to obtain higher levels of culture if you're together with other people. More culture can be created and more culture can be consumed. And of course, there's lots of literature about how cities increase innovation because of the random serendipitous connections between people. So we talk about networks. We generally talk about averages and talk about resilience. So normally we're looking at a network where typically we're looking at a typical level of performance, a normal level of performance, but sometimes something happens, the network is disrupted. So how big is that disruption? Well, we can think about it in terms of severity, how much loss of performance there's been, and duration, how long it takes place. And typically that creates what's called a resilience triangle of how long does it take to recover from your interruption of service back to your level of service. And if you look at the sort of the average between our normal condition and our expected condition, there is some loss of service between what we expect to what we want to happen and what will probably happen, because sometimes what we want to happen doesn't happen. So there's a reliability in our system. But of course, this doesn't have to be just a loss. There can be a sudden advantage to the system, some gain, some adaptability triangle, and our performance might be somewhat higher during that period. Both of those things can happen, and it depends on the network structure. And some of them can happen to one part of the network, which will, for example, you might have an outage in one part of the network, which means that the travel times on the other part of the network that wasn't affected by the outage might be faster, right? Because you don't have all of these other people congesting you because they are stuck behind some outage. And this happens obviously not just in transport. This is the figure is an example from an outage from Optus, which was a wireless internet provider in Australia. And this occurred in 2023. And there was steady degradation of service. And before the whole system collapsed, it was collapsed for a period of time and then eventually restored. And resilience is the ability of the network to adapt and recover. And reliability is the likelihood the network will perform its intended function under a given set of circumstances. Okay. So we tend to think about this in terms of infrastructures, but the Earth itself has disruptions. Caves are disruptions. If you are the Earth and you want a steady surface and then a cave emerges, you don't have your steady surface anymore. So Carlsbad Caverns in New Mexico, somebody produced this 1960s era postcard, which illustrates the disruption to the Earth's, outer layer of the Earth's crust, that has become a cavern and is itself a network. There are connections between these various places. Okay, we can talk about disruptions at the level of plates and earthquake potentiality. And so California in particular is noted for its earthquakes. We just had a major earthquake in Russia and Kamchatka. So these plates, we have continental drift and plate tectonics, and plates collide with each other and they go under each other and over each other. And there's points at which this happens. And so why are there plates? Well, I don't know, probably because a long time ago, meteorites or asteroids hit the Earth and put in small fractures, and those fractures grew and those fractures collided, and the fractures colliding might reinforce the network of faults where things can come together and come apart. And we see it in art. Okay, so Mona Lisa's eyes, if you zoom in, there's a whole lot of cracking going on. This is called crackalure. Artists, art historians like to look at this. That looks like a network to me. It looks like a network of a city. If you took out the eyes of this you could say that this looks like almost a grid-like network from some medieval city. Okay, this dense cracking forms, and the cracks create weaknesses at other points that if you're close to a place that had a relative weakness in the surface paint, then it might too fracture with some disruption. And then you get to see there's this whole set of paths along which this cracking occurs. Okay, it depends on material properties and so on. And it can be manipulated. If you want to make a painting look like it's an old painting, you make it cracked. You add crack allure to the painting, and then you can try to sell a forgery. So we talked about this graph, that this graph is actually the graph of the bridges of Königsberg that Euler famously described. It's a mathematical concept to model pairwise relationship between objects. It consists of a set of nodes and a set of links that are the relationship between the nodes. So the link is a ordered pair of nodes. So let's say ij, where the link goes from, is directed. It's a digraph from I to j. And if you actually look at Königsberg, this is what it looks like today, which doesn't really look like that. If you're a transport analyst, and particularly if you're doing more optimization type of stuff or network analysis, you might be familiar with the Sioux Falls network in Sioux Falls, South Dakota. And if you've ever looked at a map of Sioux Falls, South Dakota, it looks nothing like the stated Sioux Falls network. Well, Königsberg doesn't look like Königsberg anymore. The network has been simplified over time. There's a famous quote by Alfred Korzybski. The map is not the territory and the word is not the thing. The graph is not the network, and the network may or may not be reality. So we have in practice a much simpler network now than we did then for Königsberg. We can think of networks in different ways. Normally, our first way of looking at networks is we create junctions or nodes, and connections between junctions or links. But you can define the world where the connection between nodes is between junctions is the node, and the links are the nodes that are connected, or the other links that are connected to it. So AB on the top, which is your typical primal graph, could be represented as a node, and then AB is connected to link AC, link BC, and link BD. So we would draw links in a graph sense between those nodes of the network. And there are reasons you might want to draw your network, represent your network in this type of approach. We can think of hypergraphs. So we usually think about links connecting two nodes, but a link could connect multiple nodes. So this could be a higher order relationship, where it's a link if it connects three nodes rather than just two. We can think of a multigraph. And if we look at our initial bridges of Königsberg graph, this is actually a multigraph because we have two links between A and C. And you can code them differently if you want to, right? You could code F1 and F2 and G1 and G2, and then something between F1 and F2 and something between G1 and G2. But sometimes it might be simpler to do it this way. And we have relationship between pairs of entities where those links might go between the same origin and destination, but have different costs associated with them, or different states. You could think about perhaps free lanes and high occupancy toll lanes as a reason that you might want a multigraph. We can look at topologies, all right? So in the transport sector, we tend to think about regular networks, maybe not as regular and symmetric as the one in the upper left, but where we have nodes and links don't generally cross over each other without intersecting. There might be overpasses on major highways, but typically it's a planar network as well, not always. But you could have a random network where nodes are connected independent of the distance between them. I'm going to scale free networks, small world networks, and the people in the network science literature really fall in love with those kinds of things. Networks can be in series. And we can sort of think about, a woman who would bear a child in 9 months, and the child is growing over a period of time. The elements, each period of time is connected sequentially, flow. The baby is going through a series of steps inside of that woman. And there's delays and resistances. And we can think of things that are in series as supplements or complements. And of course, it applies to lots of things. The assembly line is the most obvious analogy, right? Where we have each station must finish the good before the object is moved over to the next station, and a bottleneck in one station delays the entire product. Okay, we can look at the global conveyor belt, which is how water moves across the oceans. And there's a cycle of water movement across the oceans, which takes about 100 years, 1,000 years, I'm sorry. And people have tracked this, not me. And it distributes heat and cold across the globe. It's a planetary thermostat. The jet stream moves much faster, ribbon of air that moves across the atmosphere, and shifts in one segment can propagate downward. And if you're in Minnesota, like I used to be, and the jet stream went across the Arctic and then came down to Minnesota, you would get a polar vortex and it would be very, very cold. Okay, we can think about Hawaii as the result of a formation of a network, as various plates, the Pacific Plate, moved across the asthenosphere, and periodically there would be lava that essentially magma that would come out of the core of the earth and erupt over the Pacific Plate and for a short period of time and create an island, and then the plates would keep moving, and then that would happen again. So there's a structure to this process, and there is a network, and this network is being created as part of a structure. Or an automated teller machine, where you put a card in and money comes out, and there's a whole set of networks behind that. So if one woman can bear a child in 9 months, we have a network in series. Can 9 women bear a child in 1 month? Well, probably not. We're thinking about, can this network be parallelized? So where elements create multiple paths, we have capacity and redundancy increasing, flows sum, right, across parallel links, whereas delays add in series, but you should not add flows in series. And so these are substitutes or competitors to each other. So we have this in electric circuits. And if the switch closes, there's current flowing from a battery through the circuit. The total voltage drop across a series as the sum of voltage drops across each resistor. And in parallel branches, the voltage drop across each branch is the same and equal to the battery's voltage. So we have hierarchy and modularity in systems. In this case, we have lower level systems that feed into higher level systems, and these occur in all sorts of systems. We have centralized and decentralized systems, and this goes in politics, this goes back to the formation of the US government and the debates between Jefferson and Hamilton about the powers of the US federal government versus the states. And Jefferson was an advocate of decentralized power, and Hamilton famously of centralized power. But this occurs across a lot of fields. It occurs across medicine. It occurs across whether we need to go to work to commute to be together in a centralized place, or we can do this in a decentralized way, as we are in a sense with this conference, BTR. Personal computers versus mainframes, open source software versus proprietary software, solar power versus nuclear, micromobility versus trains, and so on. And this is one of the debates that's facing the world now about the production of goods, and how much of the production of goods be centralized in order to achieve economies of scale. So everything in the world of a particular kind is made in one place. I saw a story yesterday about a town nicknamed Sock City in China, where 1/3 of the world's socks are manufactured. That's pretty centralized in terms of production. Or we could think of a decentralized, where we would have a sock factory in every town. So at least in every country. So these are kinds of questions that are affecting global trade arrangements. We have an internet backbone, which is decentralized. And if one link goes out, hopefully there will be other links to pick it up. We have a movement in place hierarchy, which classifies links as high speed and high capacity for movement, or place-focused streets that prioritize local access and pedestrian activity. And we've had a hierarchy of roads for a long time, but it's getting more grounded into planning theory now. Birds follow on flyways, and they can be tracked. And so these flyways are forming networks, and we can see how the different birds are moving in general corridors where they expect there to be food because there was food last year, let's say. We have scaling laws. So this is the famous Disney flywheel document. And so the idea, Walt Disney probably drew this himself, and he saw the synergies, as we would say in business, between his films, TV, music, and most particularly Disneyland, and that the films would create IP, intellectual product for Disneyland, and Disneyland would create people who wanted to go and see the films. And so there was this mutually beneficial flywheel effect. This is a network effect. The more that there is, the more that you want. The more consumers there are, the more demand that there is. And this creates economies of agglomeration if we do this in terms of a city, where there's a high level of concentration in the center of a city. And that's because people who locate in the center believe that they are more productive because they locate in the center. And there's lots of reasons why they might be more productive. There's more innovation, there's division of labor, there's specialization. But of course, that means that the costs will be more expensive. And so some people or firms will choose to locate not in the center, but in the periphery. And they might not get as much economies of agglomeration, but they save on the negative externalities in the land costs. And we can see networks change over time. So we have generative growth models where function follows form and vice versa. These have self-organization. We have sequential connection models. Okay, so where we have high-value links that are reinforced and low-value ones are abandoned. And we can successfully replicate historical evolutions. And this is work that was published based on Feng Shi's dissertation. You can look at evolving transportation networks. Hopefully your library has a copy or can get you one. So if we look at sort of the early models of preferential attachment, now this is not the earliest model of preferential attachment. It is the most famous one. So starting with some distribution of nodes, a new node is added to the system at each time step where the new node is linked to existing nodes with the probability that's proportional to the number of nodes that are already connected to that node. All right, so the rich get richer. If you have a lot of nodes that are connected to you, you're more likely to attract a new node. All right, seems plausible as a type of network growth. It doesn't really account for scale economies. It doesn't account for capacity and saturation. It doesn't account for any kind of connection costs such as distance. So you could try to generalize that model with additional factors. And then we might get a somewhat more realistic model, certainly one that would be more something we would understand in the infrastructure space. Okay, so the idea of the rich get richer, this is often called the Matthew effect. If you read the New Testament of the Bible, there's a quote. This is from the Revised Standard Version, but lots of translations have similar quotes. For to everyone who has will more be given, and he will have abundance. But from him who has not, even what he has will be taken away. Doesn't sound great, but he who has will be given. This is hub and spokes in aviation. A hub airport will have more flights connected to it. And why is that? Because there's more connections possible and people want to be able to fly when they want to fly, and they are able to fly when they want to fly if there's more connections. If you only had direct flights between cities, you wouldn't have them very often because you'd have to wait to get enough demand going from point A to point B, or in this case, I guess, from point A to point G. And since there's very few people perhaps going from point A to point G, but there's lots of people from A, B, C, D, and E who are going to G. If you go to the hub and then aggregate your flows with all of the other flows that are going to not just G, I, and J, you can take a trip to a second hub and then transfer to G, or maybe you can fly to G directly. So we have hub and spokes in all transport systems, and really many systems, not just transport systems. We have this type of pattern in ant trails. So my colleague Tanya Lottie studies ants, and she's looked at the evolution of ant trails over time. That looks like a network to me. What's causing this network? Ant pheromones. So they go, they find food, they come back, and they're laying down pheromones so that other ants can follow the same track to it. And they follow generally similar paths and reinforce each other, because the more ants that are going, the more pheromone they lay down. And then when the food is done, the ants will come back, but not lay pheromones. And then those pheromones will evaporate and the network will disappear over time. And so we can think about network growth. So ask, why do networks expand and contract? And do they self-organize into hierarchies? And are roads really an emergent property? And how can we predict the location of network expansions and contractions? And how can this improved knowledge help in planning transport networks? Right. So this is some work that I did with Banu Yera for his master's thesis, published in a couple papers, precursor to the Evolving Transportation Networks book. And so let's imagine we have a system divided into two layers, a land use layer and a network layer. And the network is a directed graph, and the land use layer has small blocks, and each of those blocks has some number of trip makers. And we have a strategic transport model, what Americans would call a four-step transport model. Doesn't matter what transport model you have, just some model. And our exogenous factors are economic growth and land use dynamics, but we can fix all of that for the time being. And our endogenous factors are travel behavior and link maintenance and expansion costs and network revenue and investment rule and the amount of investment that'll be made and induced supply and induced demand. So if the network is faster, there'll be more travel. And if the network is slower, there'll be less travel. And if the network is got a lot of demand, there'll be more construction. If the network doesn't have much demand, there'll be less construction. And so we model with land use and demography, and we have different kinds of distributions, but let's start with a uniform distribution to make everything simple. And trips come out of a block, and they are assigned to the nearest network node. And there's some sort of impedance. You're more willing to travel short distances than long distances. And we have some sort of typical impedance function. There's nothing special about this impedance function, I don't think. In this case, in the example that I'm going to show, we're just going to assume travelers choose the shortest travel time path. There's no specific congestion effects, but obviously one can do experiments with congestion. And the network raises revenue, and it raises revenue proportional to the length. There's a toll that's charged that's proportional to the length of the link and the speed of the link. And the revenue is proportional to the toll multiplied by the flow. And the cost of maintaining the network is a function of the length, the flow, and the speed of the network. Higher speed networks are more expensive to maintain, more flow results in more wear and tear, and longer links are, of course, more expensive. And we have a simple network investment model, which says that the speed on the link this year multiplied by the ratio of revenue to costs will give us the speed next year. So if revenues exceed costs, the network is expanded. And if revenue are less than cost, then the network is contracted. And so I'm using speed here as, in a sense, a surrogate for capacity. But we make improvements to allow vehicles and people to travel faster on this network. So we start with as simple as possible. All links are identical. The speeds are 1. The land use is identical. All the cells are 10. There's a friction factor, omega equal to 0.01. And we have some parameters for the model. When it's important what these parameters are, otherwise things may or may not be stable. But revenue is proportional to the length of to the flows and to the length and the speeds. And the infrastructure costs have some economies of scale associated with them. And so we start with a network. Let's say it looks like this, okay? And our initial, we lost slide 0. Our initial network is uniform. And then we have, after an iteration, most of the network is uniform. Some of the network is at a slightly faster speed than the rest of the network. So you have links that are yellow and links that are green. And we iterate this, okay? There's nothing else exogenous about this network. We're just iterating the dynamics of the rules that I've given you. And we see the emergence of a hierarchy of roads, and just following the Matthew effect, the links that have are faster, and then they attract more traffic, and the links that don't have are slower, and they attract less traffic, and they are allowed to deteriorate in speed. And eventually our network gets a beltway, a second beltway. All of which is to say that a hierarchy, like networks themselves, emerges and need not be designed. And we can apply our network theory, or people have applied network theory to physics. Causal set theory says that space-time is discrete, and it's a set of causally ordered events, and their events are influenced only by their immediate causal path, and it's modeled with a hypergraph. And future states require step-by-step evolution to work them out. There is computational irreducibility. So Stephen Wolfram, if you've ever used Mathematica, you should know who Stephen Wolfram is built a whole alternative physics evolutionary process based on this idea. So to summarize, everything is a network. Form shapes function, and function reshapes form. And transport researchers, my guess is what this audience is, are uniquely positioned because they have expertise in physical networks to understand how the world works. And with that, thank you. I'll take questions.
Thank you so much, Professor Levinson. Sorry. It was very insightful presentation. I don't see any question here. So I encourage actually everyone to ask your question. I think you should be able to even unmute yourself and ask questions.
Yep.
I think
they are able to unmute themselves now.
Thank you. And also,
Okay.
I wanted to apologize. Yikan Wu is the Zoom coordinator. Previously, I mentioned Nasser. Nasser is doing the second, basically the first panel afterwards. Thank you, Yikan.
Oh, good. All right.
Okay, so if there's not, okay, I don't see any question. Perhaps, David, I can ask a question. I have plenty of questions, but let me just ask the first one and then I hand it over to attendees. So that kind of causality between supply and demand, that was something that I, especially when you were talking about the time series of the concept of network. We see some methodologies like, for example, system dynamics that I'm kind of now getting myself familiar with. Do you reckon, can we include more of those causality feedback loops between the supply and demand, particularly with the time series, particularly with the lag of, for example, the effect of providing supply, let's say a network link, and then the impact on the demand, because like, for example, for forest step, we have a feedback loop and then we run it like iteratively, or for example, in some other methods, it could be inherent. What's your take on some of the more innovative methods to take into account for that causation between supply and demand, that chicken and egg problem?
Okay, so the first thing I will say on empirical work, if we're not using time series, I don't know what we're doing. Okay, so we should be looking at data over multiple points of time. I don't know why. I understand why the first transport survey was done, we didn't have time series. So back when the first travel surveys were done in the 1940s, and you wanted to build models in the 1950s, maybe you couldn't do time series. Well, we've been collecting data for decades, so we have time series information on lots of things now. So for all of our empirical work, it should have time series, which allows us to do causality. When we are doing models like strategic transport models, four-step models, we should have feedbacks between supply and demand, and that should take place not instantaneously and maybe not in equilibrium, depending on the structure of the network that you have, but there should definitely be consideration of how does supply change demand and how does demand change supply. Obviously, it depends on what kind of scale of intervention that you're making as to the magnitude of this effect. But if you're planning major new facilities, they're going to change demand in a significant way. And if you consider your demand exogenous and not sensitive to the change in the network, then you're going to not just be out of equilibrium, you're going to be wrong, and you're going to be wrong for obvious reasons. So I think we have to be thinking about the interaction between supply and demand and form and function throughout everything that we are doing. And it should be first nature to us to be doing it rather than something that's like an add-on. It should be built into the initial process, and that the feedbacks weren't built into the initial transport planning models in the 1950s. All right, I mean, it was the 1950s, but by the 1960s, people understood this conceptually. And we're in the 2020s, and there are places, I won't name them, but I live in one, where the official transport models don't properly account for the feedbacks between supply and demand.
Yes, thank you. And for the non-equilibrium, I also like that also kind of insight. We may not actually need equilibrium, right? Necessarily.
Not everything's in equilibrium. Now,
Yeah.
I mean, traffic assignment is probably near equilibrium. But
Agree.
And supply and demand in transport is in equilibrium if you assume the land use is fixed. But if you go one step beyond that and say, well, the land use really is in a system with the transport system, which it is over the longer term, maybe not, one day away, but if you're going to go out a couple of years and you're building a major system, then the land use is going to change. That's very much a non-equilibrium system, and certainly not a unique equilibrium, and it's very sensitive to initial conditions. I don't know how we can accurately model that, honestly, but if you just ignore it, I think you're going to be doing a worse job than not trying to think about the question.
That's correct. David, we have one question from John Niels. Question for you. Given that the shape of evolving urbanization is highly influenced by the road network and road vehicles, what's your opinion of government efforts to reshape urban activity around high-capacity rail links connecting nodes of high density?
So I think in large cities, in Sydney, it would be an example of this. There are, and here it's an official policy now to be intensifying development levels around stations. And I think that's a rational way if you're trying to think about how to, certainly if you're trying to optimize the use of the rail system, building high density development around train stations is the logical place to be developing things. And why would you want to maximize the use of your public transport system? Well, if you plan to be a large city and you want to move lots of people, then public transport is going to be a lot more efficient at doing that than, say, private automobiles. Not necessarily than bicycles or electric bikes, but than private automobiles. So higher density is sort of a prerequisite to having high capacity mass transit. And especially if you think CBDs are still going to be important. Now, on the other hand, we have this tension between centralization and decentralization, and CBDs were important for, the last 150 years or so, but there's no guarantee they'll be important in the next 150 years, and they might be, but I'm not 100% convinced of that. And public transit does a lot less, is a lot less effective at serving dispersed origins and destinations. And so if you don't have an employment center that's very high density, then trying to retrofit a high capacity public transport system is going to cost you a lot of resources that probably could have been spent elsewhere on other types of investments. So these systems are interrelated, and in part it depends on yours and everybody's belief about the future as to what we should do. And then based on what we do, that's going to shape the future. And so if we build a public transit system that serves a CBD, we're probably going to have a stronger CBD than if we don't build a public transit system that serves a CBD. But there's no guarantee that the CBD is going to be as strong as we think it will be in 20 or 30 years, regardless of whether we reinforce it or not.
So may I follow up?
Sure.
Hi, David. John,
Hi,
John. I'm talking to you from, of course, the west coast of America. So talk about where new forms of transportation may affect the decision to go one way or another. As you know, I'm sitting in a city that's trying to spend $150 billion to reshape activity around a light rail network, trying to push out to get 3% or 4% or 5% is all they seem to get at 2050 in terms of the market share. But we're just wondering if we're missing some bets with a road network that's going to handle robo-taxis, and where maybe city nodes, suburban nodes can be served by electric urban air mobility, which a lot of people seem to be working on. So what's the technology overlay, the transportation technology overlay on decision making do you think should be taken into effect now?
Yeah, so working backwards from what you were talking about, and I'm not sure I'll hit all of the points, but I'm highly skeptical of urban air mobility moving significant numbers of people.
Okay,
I'll just
fair enough.
say that,
Yeah.
and
Check.
well,
Move on.
for lots of reasons. I think it depends on the density of your city and how many people are going into your CBD every day as to how you want to organize it. And so if everyone's going into the CBD, high capacity rail transit's great. If you are in an American city where you already don't have a lot of people going into CBD, and even in Sydney, which is a fairly dominant CBD, only 15 to 25% of workers will work in the CBD. And of course, not every one of them commutes every day, but that's a lot of people. So you want to be able to look at alternative forms. And if people are going to be more in a work from home, work from the neighborhood type of context, how you reuse your road space to serve that and serve that in a sustainable way is important. I don't think that everyone driving to a CBD, even if it's in a shared autonomous vehicle, is necessarily the way of the future. But if you can get those vehicles down to a small enough scale and they're basically, automated bicycles, then you might have enough space to handle that. But not if everybody's driving in a 6-passenger automated SUV. So I think there's a lot of context that affects this answer. I'm not hopeful about the American urban condition, but I'd love to be proven wrong about my hopes on that. I think other places in the world and what the right solution is technologically in East Asia or Australia or Europe is not necessarily the right decision in the Pacific Northwest. And what's the right decision in Seattle CBD is not necessarily the right decision for Portland or for the Seattle suburbs. So I think a lot of the context is important here and will lead to different outcomes, even with the same rules. But it depends on what you think is going to happen about how many people want to get together at a given point in time. And the internet, and especially mobile internet, and especially high bandwidth internet like we're using now, has changed the need to be present the way it was essential 50 years ago.
Although you will admit, of course, that co-presence that is face-to-face, has some characteristics that are very difficult to achieve even with high bandwidth, correct?
Indeed.
Yeah.
This isn't a substitute for us all being in the same room, but it's much lower cost than us all being in the same room. So
sure.
That's, I think, a trade-off that we need to think about. And while we may have, during COVID, we may have leaned too far against being in the same room. I don't know that we found our equilibrium position in this, and I don't know that there is an equilibrium because the technologies will keep changing. But the downtown is a phenomenon that's 150 years old. It's not a perpetual state of humanity, and I don't know that it will continue to be a perpetual state of humanity. So
thank you for those observations, David. Very, very nice.
Thank you so much, David. Let's just put your hands together for David, like virtually. Thank you, David. So I think at this point, we are moving